Good afternoon everybody, and once again welcome to the Volterman webinar series. My name is Ian Richardson. Martin Muxworthy and myself will be the presenters today. Just a quick note on some housekeeping, if you like. On the left hand side of your screen you'll see a small box that says Chat Q&A. In this box you're able to submit a question just by typing it in there. What the presenters will do is we'll have a look at the question, and if it's something we can answer straight away, we will. If it's going to involve a lengthy response, we will advise you that yes, we've got the question, we acknowledge it, and we'll have a look at that question towards the end of the presentation, just to so that everybody knows what's going on. So if you can fill that out, that would be fantastic. We'd love to hear from you. Thanks again for committing the time to take part in the webinar. At the end of the webinar, after Martin and myself have completed our presentations, there's a very quick 30-second survey that we ask you to participate in and just give us some feedback on what you think. So if you don't mind, we'd really like to get your comments. So at the moment I will pass you over to Martin, and he's going to give us a bit of a talk on product compliance from the cables perspective. Thanks, Martin.
Thanks, Ian. Welcome again, everyone. As Ian said, my name's Martin Muxworthy, and I'm going to be talking about product compliance and the cables perspective. We've probably all heard about product compliance and the publicity recently surrounding some recalls of non-compliant building cables. What I wanted to do was explore what does compliance actually mean as far as a cable is concerned, and what I'm going to try and do is relate that to cable performance. I'll explore this topic in detail. Hopefully it will be interesting, and it is a rather dry topic, but I'll try and make it interesting for you. Okay, let's move on. Ian gave me a brief introduction. I'm from Nexans Oldex. I'm a senior engineer, electrical engineer, and I'm located at the Tottenham facility in Melbourne. Generally speaking, for electrical products used in Australia, the fundamental avenue for compliance is the wiring rules, commonly known as AS3000, commonly known as the wiring rules. AS3000 in essence is an installation standard, and it's a legally mandated document, and therefore the risk of non-compliance is not only unsafe, it's also illegal. The document defines the principles upon which electrical installations must be designed and installed in order to protect people, livestock and property from the risk of electrical shock, fire and physical injury hazards. In terms of cables, the wiring rules makes direct reference to a number of Australian and New Zealand standards as a principal means to ensure that its scope is fulfilled. When it comes to low voltage cables, there are two notable standards that are referenced in AS NZS 3000, and these are the AS 5000 series of cables. 5000 Part 1 covers 0.6/1 kV rated cables, and AS 5000 Part 2 covers a 450-750 volt rated cables. And the pictures there suggest what products that they apply to. So the 450-750 everyone would be familiar with, the TPS type products, and the 0.6/1 kV rated cables are the orange circulars. What I've tried to do here is break down the different essential functions that a cable has to perform, and then what I'll do is I'll go through the various testing and checking that is done in the cable factory to ensure that the cable meets these basic functions. There are four functions or categories that the cable must be able to perform. Some will be pretty obvious. Obviously the cable has to be able to carry the required current. Cable must be able to hold the voltage that it's designed for, and in other issues like the cable has to be able to withstand the handling and installation stresses, mechanical stresses that are consistent with the application that the cable is intended to be used in. and the last one, and probably the most important, has to be able to provide a long service life under normal use. Obviously this can vary depending on the cable type and application, but typically for static, building type cables, there's an industry understanding that this should be about 40 years or so. So how do we ensure that compliance is obtained that enables these functions to be met? So we'll look at that in the next few slides. And one thing I should emphasize is that when we go through all of the tests and checks that are done on cables, not all the tests need to be performed on every drum or length of cable that's manufactured. The Australian standards define which tests must be performed on each length, and these are called routine tests. And then there are those tests that are performed on, say, samples of completed cable or components taken from completed cable, and these are, as the name would suggest, called sample tests. And there are those tests that need only be performed once when, say, developing a new product or a new process, or say trying out a new material, and these are type tests. And in the case of the type tests, these are done to confirm the ability of a cable factory to manufacture a specific type of cable before a factory is allowed to actually start supplying a cable on a commercial basis. And type tests don't need to be repeated unless changes are made, say, in the materials or the way that the cable is manufactured. So now looking at the ability of the cable to carry the rated current. So how does the Australian standards define these properties and ensure that compliance is met? Quite simply, the electrical resistance of the conductor must meet a specified value, and that's defined in another standard, AS/NZS 1125, which is obviously referenced in AS 5000. And for each nominal conductor size, the standard tabulates the maximum DC resistance at 20 degrees that each conductor must meet. So this is the value that we measure. We don't actually have to measure the area. The area is not critical, and this is a very important and probably often misunderstood issue. For example, a 35 square mil copper conductor does not need to have 35 mil of copper in it. It only needs to meet the specified resistance value. And neither is the diameter of the conductor important as far as compliance is concerned. Smaller diameter conductors such as compacted or larger diameter non-compacted do not matter, as only the electrical resistance is a mandatory property that needs to be measured. When we look at the impact of resistance and if non-compliance happen to occur, the impact of resistance on current rating is quite small. Current rating is proportional to the inverse of the square of resistance, so therefore an increase in resistance of, say, 4% results in only a 2% decrease in current rating. So it's quite small and not a significant influence on this particular performance aspect of the cable. The other things that define the current rating of the cable are the materials that are in contact with it. So if a cable is rated at, say, 90 degrees, maximum continuous conductor temperature, then that material must be compatible with that operating temperature. So in the case of, say, a 90 degree rated cable, then we would use, say, an X90 or XLPE material on that conductor. There are some higher rated cables such as 110 degree rated cables. These are commonly used in fire rated cables, and accordingly these must have an insulation that's compatible with this temperature, and typically this could be something like XHF110. The next few slides will detail how we check for compliance of these materials, and it's quite a complex subject, but we'll have a look at this a little bit later. And the next performance aspect we're going to look at is the ability to hold rated voltage, and it sort of goes hand in hand with the cable's ability to withstand handling and installation mechanical stresses. A variety of cable insulating materials exist in the cable manufacturing industry. all having differing properties, but all having the primary attribute of being suitable as an electrical insulating material. The differences lie in such things like cost, processability, dielectric performance, mechanical strength and flexibility, to name a few. Some of the common materials that are nominated in AS 5000, for example PVC, V90, XLPEs, I've mentioned before the 90 degree and 110 degree versions, and there are various rubber materials, EPRs, RHF110s, and so on. Some of the materials used in reduced fire hazard cables, like the fire rated cables, they could use either thermoplastic like PVC or cross-link materials such as XLPE. Due to the differing electrical and mechanical properties of each material, Australian Standard 5000 nominates differing requirements, and all of these requirements are detailed in another document called AS 3808, and this is the document that defines all of these tests and checks that need to be done on the materials to ensure that their performance can be met. The first, to check that the cable can hold its rated voltage, I mean there's a number of electrical tests that are done to check this. And again, I mentioned not every test is conducted on every drum, but we'll just go through some of these tests quickly. When cable insulation is actually extruded, the extruded insulation will go through a spark test machine, so that the purpose of that test is to check for defects in the extrusion process. So that's actually an online test that happens as the extrusion is happening. There is then various tests on finished cables, such as an AC test at 3,500 volts for 5 minutes, and that is largely a routine test, so that would be done on every drum. And then there are other tests like the 1.8 kV test for 4 hours, which is a type test, and other electrical tests that are done as measurement of insulation resistance. And what you'll see from the magnitude of these test levels is that common practice when it comes to testing of virtually of any nature is subject the cable or material to stresses much higher than that which you would experience in normal operation. So that's a very common test procedure. Now, to further check that the cable can hold its rated voltage, we need to measure the thickness of the insulation. Probably fairly obvious, but what may not be so obvious is how the thickness is measured, and the fact that the insulation thickness does vary depending on conductor size. So even though we might be talking about cables of the same voltage, the insulation thickness does vary with different conductor sizes. For example, the insulation thickness on large conductor sizes is greatest, and that's just due to the greater risk of mechanical damage during handling of large and heavy cables, for example. And the insulation thickness for XLPE is not as great as that of PVC, because XLPE has superior electrical and mechanical properties compared to PVC. The improved electrical properties of XLPE is just a result of the chemical makeup of the material, being almost exclusively polyethylene, and polyethylene has an excellent dielectric properties and excellent dielectric strength compared to PVC. PVC is a blend of a number of ingredients, of which polyvinyl chloride is one, and much of the improved mechanical properties of XLPE comes from the fact that it's a cross-link material, whereas PVC is a thermoplastic. In essence, cross-link materials are more thermally stable compared to thermoplastic materials, and will not flow when subjected to higher operating temperatures. So how do we measure insulation thickness? Well, you could probably figure out that when you're extruding plastics on odd shapes and conductors where the strands poke into the insulation, it might be very difficult. But the method of measuring the insulation thickness or the sheath thickness, for example, is well established. Basically, what we do is you take slices of the insulation or sheath, and you measure the thickness by taking 6 measurements at locations where the material is thinnest. So where the wires poke into the insulation, you would take 6 measurements around the slice of material that you cut. You need to have some sort of optical magnification equipment. Needs to be at least 10 times so that you can read down to about 0.01 millimeter. And what you do is, from the 6 measurements, the lowest value is taken as a minimum at any point, and the arithmetic average of the 6 measurements is taken as the minimum average thickness. And these 2 values are the ones that compliance is confirmed, and they are required by nearly all cable standards today. I mean, these measurements used to be done manually, but today modern manufacturing techniques has seen the introduction of automated electronic measurement systems, so that makes it a lot easier, a lot faster, and improves the repeat accuracy of the measurement. Moving on to looking at how a cable is able to withstand handling and installation stresses and provide a long service life. The long service life part is extremely important. I talked about AS 5000. It references AS NZS 3808, and this standard details a large range of material tests. The test methods themselves are defined in another set of standards called AS NZS 1660. These tests predominantly involve mechanical testing, and they involve things like stretching materials, breaking them, bending them, and I'm not talking about just conductors, I'm talking about the plastics themselves. So bending and breaking and squeezing and indenting and so on. Some tests are done on materials as they come straight off the cable, but others require special aging of the material at an elevated temperature. And this elevated temperature or aging regime is aligned with the temperature rating of the material and serves as that principal means to check that the long-term performance and stability of the materials are met. So, some slides about how we do mechanical testing of cable components. The first set looks at how we check that, say, the material is strong enough and pliable enough. And what we basically do is, if the cable sample that we want to test is large enough, we cut dumbbell shaped test pieces out of it. But for small building products, for example, the test piece will be a little bit too small, so we test the extruded component itself, obviously with the conductor removed, but we test the extruded tubular component itself. So what we do is we subject the test piece to a tension in a tensile test rig, and we measure the maximum load that can be applied to the test piece. And then we also stretch the material until it breaks, and then we measure the elongation. And the pass criteria for different materials varies according to the material type and is documented in AS NZS 3808. And what I've done on the next slide is tabulate some of the common materials that are used in cables and the test pass criteria and some of the aging regimes that are done to check the long-term performance of materials. So what we can see from this table is along the top row some of the common cable materials: V75, V90 PVCs. Then I've also listed the 3 V75s and 3 V90s. These are the easy tear materials that electricians would be quite used to on the TPS type products. And then we've got the 5V90 sheaths and XLPEs. Along the left, we've got the test pass criteria and the aging regime for each material. The elongation values are much the same for all PVC compounds, and is slightly higher for XLPE. The tensile test requirements, as you can see, the easy tear materials, they are a lot lower than the other PVC type materials, and as the name suggests, because they have the lower mechanical strength, then they're much easier to tear and strip from the cable. What we also take out of this table is the aging regime for each material. If you compare the 75 degree rated PVC versus the 90 degree rated PVC, 75 is aged at 240 hours at 110 degrees, and this is done in an oven at a constant temperature, while the 90 degree material is aged for a much longer period, 504 hours, and a slightly higher temperature. The main difference in how PVCs are formulated to produce a V75 versus a V90 is the plasticizer that's used in PVC and its temperature rating. Plasticizer is needed to ensure that the PVC is soft and pliable and can be used for insulating and sheathing of cables. It's just one of the compounds that make up PVC, along with things like fillers, stabilizers, and some other materials. And I mention this as it is a point of difference that has caused some imported products to be found to be non-compliant. So this is a very important aspect. The bottom two rows, what they show us is after the material is aged. These gives us the pass criteria, and what they mean is that after the material is aged, the tensile property of the material can be no less than 75% of the original unaged value, and the elongation can be no less than 65% of the original unaged value. I guess maybe it's not so obvious why that all this mechanical testing after aging is performed. Aging of plastics is commonly characterized by loss of mechanical strength. That's the one. That's how we check that that aging has not occurred. And what happens is that they become hard and brittle. So they serve as a very useful guide to estimate their long-term performance. The aging regime is derived from European practice and is designed to replicate the typical aging mechanism of cables installed in a common cable environment, but at an accelerated rate. A general rule of thumb for aging of materials says that for every 10 degree increase in cable operating temperature, the life of materials are expected to halve. And what I showed you on the previous table is how the aging regime is aligned with the temperature rating of the cable. It is this area, and this is the important point, it's this area of testing the mechanical properties after aging that the recent reports of non-compliant cable products have failed. Cable might be okay when first purchased and installed, but if it doesn't have that long-term aging performance, then it might fail in a few years simply by becoming hard and brittle. And the other point about this particular slide is that most cable material testing involves some form of accelerated aging to check long-term performance. There's a number of that's in essence the major focus of this of long-term performance of cables. There's certainly a lot of other tests that are done to check for long-term stability. Things like checking the volatility of the plasticizer, and this again comes back to because PVC is a compound comprising a number of different ingredients, we must check to make sure that it's stable. And then one of the other tests that's done is we check for loss of mass of the material, and all it's really doing is checking the volatility of plasticizer in the PVC. And we've talked about the consequences of loss of plasticizer. It'll mean the PVC becomes hard and brittle. All this test really involves is checking the mass of a sample according to a set aging regime again, or a set heat aging program, which is aligned with the temperature rating of the material, and you measure the loss of mass. And then, as I said, it checks the long-term stability of plasticizer within the PVC compound. Other tests that are performed, and you'll notice the ones I've listed so far, these are done on PVC only. Because PVC is a compound, and like I've explained, has a lot of different ingredients, a lot of them are concerned with the stability of the PVC compound. One of the other tests is a pressure test. This test is done at maximum operating temperature of the material, and is performed by subjecting the material, PVCs and other thermoplastic materials, to a cutting blade of set width with a specified force, and measuring the depth of indentation or penetration of the blade. Since PVCs are thermoplastics, they are more prone to material flow at high temperatures, and so this test confirms that the cable materials will survive, say, the mechanical forces that are typical for a normal operating environment, like forces from cable saddles, cable clamps, clips and cable ties and so on, because you don't want cable fixing devices penetrating the insulation and causing failure. Past criteria is at a depth of penetration no more than 50% is allowed. Other tests that are done on PVCs, and again this is related to loss of plasticizer, and that is to do what we call a heat shock. Basically the test procedure involves winding the test piece, and it's a sample of insulated core or cable, whichever the case may be, onto a mandrel of specified diameter, and this is aligned with the diameter of the test piece. And when it's performed on the insulation material, all other layers are removed, and the test piece is placed in a preheated oven at 150 degrees for an hour, after which it's taken out and it's allowed to cool to ambient and is examined for cracks. So it's to simulate things like thermal cycling and rapid change in temperature, and a pass is achieved if there are no cracks within the material. Like all of the other ones, it checks for the suitability of the cable material to be used in common installation conditions, and I think about where temperature cycling could occur, and it could be due to fluctuating loads, or it could be just simply due to fluctuating environmental conditions. And obviously where bends exist, stresses are higher, mechanical stresses are higher, so there would be more of a likelihood of fracture of materials at these locations where there are tight bends. And like I mentioned before, this test checks, it's called a heat shock because it shocks the material well above that which would normally be expected to occur in practice. The next test is a test that we have to do on XLPE and crosslink materials, and it's called a hot set test. It's done by a hot set test checks the degree of cross-linking of the material. It's done by subjecting a sample in a similar manner to that used to perform the aging test on insulation and sheathing materials. And you might remember the dumbbell shaped test piece that I talked about. same sort of thing is done, but this time in the hot set test, the sample is subjected to a force specified value, 200 kPa, and we measure the elongation after a set period of time at an elevated temperature such as 200 degrees. The pass criteria is that the test piece must not stretch more than 175% of its original length, and after cooling to ambient it must not have more than 15% residual elongation. So what happens is, because it's cross-linked, it will tend to reform into its original shape, and that's an important fundamental difference between cross-linked materials and thermoplastics. Thermoplastics, if you stretch them, they will stay stretched. Cross-linked materials, if you stretch them, they will tend to want to return back to their original shape. So that's how we check for the degree of cross-linking of materials such as XLPE. Continuing along the same theme, and going back to PVC now, all I've done is really just listed these tests in order that they appear in the standard. The next test is what's called a loop test, and it checks for exudation of plasticizer. Again, you'll see a lot of focus on exudation and loss of plasticizer in PVC materials. So what this does is checks for the stability of the PVC at room temperature, and checks to see whether there's a tendency for the plasticizer to flow when the material is subjected to, say, a pressure of set value at room temperature. It's performed by milling a sheet of material to a specified length and width, and then folding into a loop and left for 24 hours. And stability of the plasticizer will be observed if there are no signs of greasiness or droplets of liquid on the inside of the loop. Fairly simple test, but it's just a mechanical test that has to confirm that, you know, that the plasticizer is stable within the PVC material. So again, it's another way in which the long-term stability of the cable materials are achieved. This is the final test, and this one involves checking all materials that are used on a cable while the cable sample is actually intact. It's done in a similar manner to the tensile and elongation testing that's done on the insulation and sheath materials, but it has the intention of checking that the cable material properties don't deteriorate as a result of physical contact with one another. Some cable materials have an affinity for others when in direct contact, and this ensures that there was no loss of properties. Compatibility of cable materials is confirmed by subjecting a cable sample with all of the layers intact to a heat treatment of about 240 hours in an oven at a temperature 10 degrees above the maximum operating temperature. And then you recheck the tensile strength and elongation of each of the non-metallic materials again, and you compare them against the unaged values. The minimum pass criteria is that they have to retain at least 75% tensile strength and 65% elongation compared to the unaged values. The last slide is just a summary. I hope what I've done is given you a bit of an insight into the range of cable and material tests that are required to be performed to check for compliance with the relevant cable standards. They can be quite detailed and complex, but they all have a purpose, and I've tried to relate that back to cable performance and suitability for the application in which they're intended. The overall message that I wanted to leave you with is that Australian and New Zealand standards have well established methods for determining the properties of cable components and materials from the point of view of both short-term and long-term performance. The standards detail a range of tests that check that cables are suitable for use in typical Australian conditions and will continue to provide a good service life when operated under these conditions. In some areas, Australian and New Zealand standards test methods are more stringent than European standards, even though I mentioned before they're based on European. But this simply emphasises they're relevant to checking that they're suitable for Australian conditions. And my final message, careful selection of cable materials is critical in ensuring long-term performance is met, which is no more evident than the recent examples of imported product that had failed the long-term aging test requirements of the Australian and New Zealand standards. So that's the end of my presentation. We might just pause to see if anyone has any questions. In preparing this presentation, I thought of something that cable users and installers would probably want to ask, and that is, well, how would you know if cables are compliant? It will be difficult to tell just by looking at the cable markings or the markings on a drum. So how do you actually tell that a cable is compliant and pass all these tests that I've been talking about? You could ask for a certificate of compliance. But usually, if you get a certificate of compliance from a manufacturer, this will just simply be a statement that it complies with a particular standard. I discussed type tests, sample tests a bit earlier. Better still, what you could do is ask for a qualifying test report to the relevant Australian standard. And this is a document that will have the results of all of the tests that I've just been discussing. So you could actually check what all the values are. You could check that they're compliant. You remember that it doesn't have to be done on the same cable that you were interested in using. It only has to have the same materials and is of the same basic type. And then you could go further and you could check that the tests have been conducted by a reputable test authority. And a common example is, say, in Australia, a NATA accredited test laboratory. So that's one way that you could be definitely satisfied that a cable is compliant. We might just continue to pause to see if anyone has any questions. I might hand it over to you, Ian, and you might continue to pause. If there are any questions come through, you can always hand it back. Thank you for your attention, and I'll hand it over to Ian.
Hello everybody, Ian Richardson here, so thanks for hanging on. If there are any questions for Martin, please type them into the chat box there, and Martin will certainly address those questions. I'll start my presentation in a moment, and yeah, if there are any questions along the way then please also type those in, and we'll address them. I can't see that anyone is typing at the moment, so I can assume that Martin has covered his topic exceptionally well, which I believe he has, and I think he's done a great job on talking about compliance, and I certainly learned a lot about cables that I didn't necessarily know. So we'll move on to my presentation. That's me. Obviously I work for ABB Australia in a product and standards engineering capacity, so I've been dealing with the standards and whatnot, mainly in low voltage products for some time now. My presentation is going to talk more about electrical products and the compliance of those products. Because this is a little bit of an all-encompassing topic, and there are so many products that could fall under this particular area, I don't propose to go through exactly how individual products are tested and how they're verified, but in Australia we have certain requirements of products to comply with their respective standards, And I just wanted to speak for a while to advise everybody of this is how the current process is being done, so you have an understanding of that, and you realise what sort of things the various product suppliers are going through. So yeah, compliance is an assurance of safety. Fundamentally, that's what our compliance regime is all about. It's providing electrical safety, not necessarily guaranteeing performance of product, although when we have a compliance with a particular standard which is required in this legislation, most of those standards do have a test regime, as you would have seen from Martin's presentation. Now, whether it's a miniature circuit breaker or a residual current device or various things like that, they all have their respective product standards, usually an Australian standard, which is derived also generally from an IEC standard. Within those standards, there are defined test procedures which would guarantee a certain performance. Essentially, though, our compliance regime is more about safety. So if we have compliant products, we have the fundamental safety requirement which is required by our industry and by our general standards. This requirement is actually legislated, so it is an absolute requirement that we should use products that are compliant with the minimum standard, and this has been verified by one of the safety authorities. They also define a range of products which have to be covered by this particular legislation. Now, this is an important one. There are requirements on the installation guy, usually the contractor, that he is using a compliant product. And this can be very, very strong. So depending on which state you may be in, the various electrical safety authorities, they do go around doing audits. They can check that products have the proper compliance, and there's some markings on the product which we'll talk about later which will indicate to you when the product is compliant, and that is then your assurance that you're actually using something which is not going to cause you an issue. But it is a very broad range of products which are covered by this legislation. Looking back in some history, years ago we had a range of products that were called prescribed items, and this was defined by the electrical safety authorities. If we're talking, to keep it simple, we'll talk about a domestic installation. Something like a miniature circuit breaker up to 6 kA was a prescribed item, but a 10 kA circuit breaker was not. Something, a 30 milliamp RCD, be it a combo unit, RCBO, or be it just a straight RCD, they are covered by this legislation as a prescribed item. If you have in industry, sometimes we use a 100 milliamp or a 300 milliamp RCD. They are outside of this legislation. So that was a term of prescribed item, and up to a couple of years ago, these were the items that were required to undergo an approval scheme as defined by the safety authorities. They were also sometimes known as declared articles. This is just the definitions that are used sometimes. Essentially in Victoria, Queensland and some of the other states, they use the terminology of a prescribed item. In New South Wales, through the Office of Fair Trading, they call them declared articles. Essentially, both those terms are talking about the same group of products. Under the current system, we now have a different terminology, and we call them in-scope products. Essentially, the level 1 in-scope product is what the old prescribed items or declared articles used to be, although this range of products has been expanded slightly. Level 2 products and level 3 products are a lower scale. So essentially level 1 is called high risk, level 2 is medium risk, and level 3 is low risk. The requirements for approval vary according to these particular products. Interestingly, in Australia, we do not have any products which are legislated into level 2 at this point in time. We do in New Zealand. New Zealand has a slightly different variation to this scheme. They do have a definition of level 2 product, but in Australia we've worked with level 1 and level 3. So something like our MCB that we mentioned before would be level 1, up to 6 kA. The RCDs of 30 milliamps are also level 1. Other consumer products like hair dryers and bathroom heaters and all sorts of products like that are all level 1. The expansion to this definition also came about because essentially now the electrical safety officers are saying that any product, any electrical product that is used in a home must be registered in this scheme, whereas previously they did not. It was only the prescribed or declared articles. So now there's a requirement for the manufacturers or the importers to register these products in the appropriate way. The various regulators that we've got around the country, and you'll know some of these names because it really depends which state you're living in. So in Victoria, the old Office of the Chief Electrical Inspector is now Energy Safe Victoria. We have Fair Trading New South Wales, Energy Safety WA, the Technical Regulator of South Australia, the Electrical Safety Office in Queensland, WorkSafe Tasmania, WorkSafe NT, Northern Territory, and Environment and Planning in the ACT. So these are the fundamental safety regulators in each state, and they do all work together and they all talk together. So each one of these officers is recognising what the other officers are doing. So if we, as a manufacturer, if I get something approved in Energy Safe Victoria, which we commonly do, it will be automatically recognised because of a national recognition program by all of the other regulators. So really it doesn't matter where we get the approval because we have this recognition. So we don't need individual state approval for various products. As long as we get one and they approve it in the appropriate way, it will automatically be recognised by the other states. The other group in the background is the Australian Communications and Media Authority, the ACMA. They used to administer all radio frequency emitting devices, and they had a safety program which was called CTIC. And I'll show you in an upcoming slide what the various logos look like. The ACMA are now falling into line with all of the electrical safety groups, and they're going to have one logo which indicates that there is compliance of product right through. In general terms, if there's an electrical product, or particularly a product that's got electronics in it, it's required to comply with the requirements of the ACMA in regards to electromagnetic interference, or EMC. Generally what will happen is products that comply with, say, an international standard, there is an EMC element of that standard, and that will transpose across here, and the local importer or the local manufacturer's agent, or whatever the case may be, is required to mark the product in an appropriate way to say that it is compliant. And if the ACMA comes knocking on the door seeking to say, well, please prove the fact that it is okay, we then have to produce the appropriate documentation. So that's essentially the way the scheme is operating. We've got another group called ERAC, E-R-A-C. This is a group formed by the various regulators and safety authorities to get together, and they're trying to form a national standard and a national procedure so that there is absolute compliance across all of the states. They also administer a national database, and that in that database it's possible for any user, any consumer or any person to look up in the database according to the manufacturer or according to the product group whether this particular product has been registered and actually carries compliance. So for us as a manufacturer to be able to enter something on the database, we must be registered as a what's known as a responsible supplier, and we can list once we have all the appropriate documentation, we can list our product on there, and then it's there for everyone to see. What's happened at the moment is this particular system is recognised by everybody except Fair Trading New South Wales, who are still negotiating how they're going to enter into this agreement. So there's a little bit of discussion going on between the various regulatory authorities and Fair Trading. I think Fair Trading thought that their system was working quite well. They have various items which is preventing them from agreeing and totally accepting the new system. And I'm sure that is going to be sorted out in the near future. But it's a little bit of a complexity. Suffice to say that it still remains that if we get a product approved in one state, it will be recognised by everybody, including Fair Trading. So that brings us to the Electrical Equipment Safety Scheme, the EESS, and this is really what this national database is all about. This is a few notes from the EESS scheme. It's based on an edict of harmonised electrical safety legislation, having equipment safety rules which are uniform across the country, which generally we have. There are the Australian and New Zealand standards in the background and also the international standards in the background. Essentially all equipment in Australia and New Zealand must comply with fundamental safety requirements, and I think that's pretty clear, everybody would understand that. It must also cover any relevant standards under any applicable state, territory and national electrical safety legislation. So what the EESS arrangement means is, again, as a supplier, it's best to talk about an example. So here we are. ABB is a responsible supplier, most of the other manufacturers are. If a person is an importer of equipment directly into Australia, they are seen to be the responsible supplier. Therefore, they are the ones that have the responsibility to ensure that all of the compliance approvals have been met. What it would mean is, let's say ABB is bringing in a new RCD, and it's a 30 milliamp one. It falls under this scheme. We have to provide to one of the safety authorities, Energy Safe, Fair Trading, any of these guys, the appropriate test report according to the Australian standard. So we need to prove that our product complies with that standard through a test report from a recognised laboratory. What the safety authorities will do is they'll verify that all of the tests have been completed. They could do a verification that the actual test report is a true one, and they may talk to the respective laboratory listed on it, or I'm not sure exactly how far they take that. And once they're satisfied that all the requirements are met and the supplier has paid the appropriate fee, they will issue a certificate of approval for that product. Then we as a supplier will go to the Electrical Equipment Safety Scheme and we can register the product on that scheme, which involves another fee, and then on the national database everyone can see that this product has been approved. So in time you can come along and you can see that there's an ABB product which you want to use, it's an RCD. If you want to satisfy yourself that it has the appropriate approval, you can go to the EESS website, which is certainly available to all, and as a general public you can do a search of that particular part and verify to yourself that you are using a compliant product. These various fees that I mentioned, they're actually not just going to the government coffers, they're actually remaining with the Electrical Safety Office, and they are using these funds to conduct audit programs and do spot checks to ensure that the products on the market are actually what they say they are. So the audit program and the approvals people that are going around investigating, this team of investigators that they all have, is being funded by the program. So we're actually finding that there's a lot more strictness coming through, and we know that the officers are out there doing their spot checks and ensuring that everything is the way it's meant to be. The other way of recognising if your product is actually an approved product is, previously we had an approval marking scheme So I got as far as talking about the approval number marking. The regulators also introduced something called the RCM, which is known as a Regulatory Compliance Mark. It looks like this triangle with a tick in the centre of it. This has been a universal logo which can be used by the approval authorities. So previously we had a choice to either print the ESV and the number, or the NSW and the number, or use the RCM. When we're now moving to the Electrical Equipment Safety Scheme, we are required to use the RCM. So it will be a common mark. Also, on some of your electronic components, be it your computer or TV set or anything like that, you would have seen this other symbol called a C tick. So it's the little black dot with a tick symbol in the centre of it. This was used by the ACMA to ensure compliance for EMC. What ACMA are doing is they're now using the RCM as well. So we only have to worry about one mark, and it's this triangle symbol, which will be the common one utilised by all of industry. So that makes it fairly easy. If you've got a product which is under the legislation is known as an in-scope product, it must have the RCM on it. So it's a good way of telling that the products that you are using are actually compliant with the current legislation. If you've got any doubts, talk to the manufacturer. There is a little bit of a transition still underway, although most manufacturers should be using and applying the RCM. The extra approval is required for the level 1 products, which are in scope. They're the ones which have a higher risk associated with them, but all products now are required to have the RCM mark on them. So as we work through the transition period, you'll get to see this more and more, and this is a symbol that will enable you to trust the equipment and know that you're using something which is compliant and you're not going to have any problems with the installation that you're working on. Unfortunately, don't think this scheme extends to cables, and as Martin said, there's other ways of going about checking the compliance as far as a cable goes. Things might change in the future too because of the experiences that we've had recently with non-compliant cable. I think that's being looked at quite closely by the regulators, and we'll find out soon enough if they decide to make any change to the requirements. But at the moment, the RCM mark is used more for electrical products such as your RCDs, MCBs, all of the other products which could be utilised in a home, and that can be any appliance essentially. They all must carry this mark, although some are still using things like CTIC because of this transition period that we've got. Essentially, everybody, that is the end of my presentation. Once again, I'd like to welcome any questions if anybody has got any, and we'll just pause for a bit of a moment to see if any questions come through. Please also, before you depart, we will be initiating a survey, so we'd love to get your feedback for the Voltiman people to see how we can make these sorts of presentations a little better for the future and make sure we're hitting the mark for what you're wanting to hear. So just pausing for another 10 seconds or so to see if a question comes through, and then we'll go towards the survey.